Hello and welcome to the following video. I'm going to explain complex numbers as exponents. What happens when I have a number to the power of a complex number. But I'm going to first ask a question, like really the idea of a complex number, is that something that somebody just made up, or is it something that somebody discovered? And this is, I think, a question that you should think about, because ultimately, what's maths anyway? Is it something that somebody made up or not, or something that somebody discovered? You'll find that people have different opinions in this, and I think this is a good moment to bring this up. So think about it, we can talk about it in class. So why do I bring this up? Because, so we came up with the idea of square root of -1 is equal to the imaginary number, and we learned how to add, subtract, and multiply and divide these numbers. So when Euler, here he is, when he had that, but that wasn't quite enough for him, because he knew that there were more operations he could do with normal numbers, with real numbers, and he wanted to be able to do it with complex numbers. So he set up on the idea of figuring out what this thing meant, what 2 to the number of a complex number is. And I'm going to explain that to you, how, perhaps not exactly how he figured it out, but how he defined it in a way. I mean, how that definition works. And it's interesting because it seems that it's actually just made up. He just came up with a definition because why not? You know, he could have defined something completely different. But as we move on, you're going to find out how it wonderfully fits in every other field of mathematics. So maybe he discovered it. That's why I bring that up. So if we look at the idea of 2 to the power of a complex number, so 2 to the power of a plus bi, where a is the real part and b is called the imaginary part. Before we set out to think like Euler thought, let's just break that up for a minute and realize, well, this thing is just going to be this thing. And 2 to the power of a, 2 to the power of a here is just going to be a real number. And what I'm really going to have to figure out is 2 to the power of bi. What is that thing going to be? That's going to be what's really important here. So let's define what 2 to the power of bi. So, okay, how do we do it? Okay, I have a number a. Let's call this the number a to the power of bi. Great. How did Euler kind of did it? It's not exactly what it did, as I said, it's just to give you an idea. Okay, let's start with a completely different supposition. Let's start imagining that I have a complex numbers and its modulus is just going to be 1. Why not? Let's start off with that. If that's the case, let's suppose now, another what if, not only that's what if, let's suppose also that I can actually write that complex number in this form. So, okay, since the modulus is 1, that's okay, because you know that, great, so all numbers that have modulus 1, you should know by now that this is going to be a way in which I can write it, where theta is just going to be the argument. So, what if I can write it in this form? Now, this might still not look at it to you like this thing here, but that's okay. We're getting there. So my two what ifs, what if I have a complex number of modulus 1, and what if I can write it in the following way? Let's first get rid of the first what if. If the modulus is not 1, then if this happens, right, if this is okay, then I can actually write any complex number in this form, right? I just multiply by the modulus and I will get to that complex number. And it makes sense that this times r will give you what I had before times r. So okay, the first what if, we got rid of it. Just wanted to use that to give you an idea of how we get here. Great. So now we have this one left, and we still don't have this. So how is that going to work? You'll see in a minute. So here's kind of the genius idea. Suppose that a and b are constants. Okay, we have that I have a to the power of k theta here, but a and k I know are going to be constants, right? So what happens if I take a derivative here? Now, a lot of you don't know what derivatives are yet. Some of you will, some of you won't. It always happens. Now, don't worry about it. We're going to revise this. If you don't know, just remember that derivatives are just something I do to a function. I change it. And what I change it into is another function that's going to give me the slope at any point of that function. If you still got very confused about that, even simpler, a derivative to differentiate or to make the derivative the same thing is just something I do to a function. That's all. But you know, if I do the same thing to the function here and do the same thing to the function here, then, which is what I've done here, those two things are going to remain equal. That's an important thing to know. So I make the derivative from both sides of the equation. And the important thing is to realize that this thing here, if I take an I as a common factor here, this side, I'm going to be able to rewrite it like this. Now think about this for a second. I times cos theta is going to give me this part here, and I times I is going to give me -1. So this thing is the same thing as this. And here comes the genius idea. Well, if I say that K is going to be I, and I say that A is going to be the number E, then what I'm going to end up with is the same thing on both sides, right? Which now I know that for that number A, so if that the base is E, and if K is the imaginary number, then I'm going to get the same thing here, which means that really I can write a number in the polar, in this form. I can write this from CIS into this form here. And this thing here is going to be Euler's formula. It's quite an important achievement in maths. This is Euler's form, and what with it? What do we do with it? Well, two things mainly. First of all, it's just a way to summarize, another way to write a complex number. Rather than have to write three letters, CIS and the argument, I can just write two letters, the E and to the power of I. Not much of a summary, but it's going to have some advantages, and you'll see it. But essentially, a complex number, I can also write it in this form here. That's advantage number one. So again, I will go back to the first question. How can we actually put a number to the power of a complex number? Because now, like, okay, I know what e to the power of a complex number is. What about 2 to the power of a complex number? If I have this thing here, first let's start off with what I have. I have an actual complex number, not just an I here. Well, remember, this is just going to be e to the power of 2 times e to the power of minus I. So I would have a complex number where the modulus is e to the power of 2 and the argument is -1. So what if it's not e? What if it's a different number to the power of a complex number? Here's an important logarithms trick that you should know. And this is actually a formula you have in your formula booklet. So the number 2, I can rewrite it, and this might sound like the worst idea ever, as e to the power of the natural logarithm of 2. Now, why is that right? Why can't I rewrite 2, my simple, wonderful, beautiful 2, into this e to the power of the natural logarithm of 2 expression? Why can't I do that? Because, so natural logarithm of 2, remember what a logarithm is the same thing as asking, hey, what number to the power of e gives me 2, right? So e to the power of whatever this gives me 2. Well then, whatever this gives me, I don't know what it is, but when I put e to the power of that thing, well, I'm going to get 2. That's the idea. That's why I can rewrite this as this. So if I have to calculate 2 to the power of 3 plus I, well, I can write it like this, so 2 to the power of 3 times 2 to the power of I. And now to turn this to base e, I just have to rewrite this whole thing like this. Now I can multiply these exponents, and I'm going to get it in this form. So simply, this is just a complex number, so with modulus 8, an argument, natural logarithm of 2. So 2 to the power of 3 plus I can be rewritten as 8 times e to the power of I, natural logarithm of 2. Or it's the same thing, 2 to the power of 3 plus I is simply a complex number with modulus 8, an argument, natural logarithm of 2. That's how we use Euler's form, and that's what a number to the power of a complex number means. Essentially, all really I'm going to be doing using this for is to summarize polar notation even further. So these two expressions, I can rewrite them like this, and this calculate the modulus and the argument. That's all it really is, and makes operations a bit quicker I can multiply stuff, I can add the arguments, and it kind of makes sense because, if you think about it, well, I'm adding the exponents, that's something I'm familiar with, and I multiply the coefficients, that's something I'm familiar with. So this kind of looks a bit more like our normal algebra. Great. Now, before I finish, sorry for the long video, before I finish, let me go through actually back to our initial debate. So think about it. Is this something that Euler just made up, or is it something that he found out? That's something I would like to talk about in class, but before we finish, I want to show you something that a lot of people think is actually quite beautiful. Let's see if you find it interesting. So Euler just came up with the following idea. Okay, so I going to assume that the modulus is 1 of the complex number. So again, I simplify to this, my Euler's form. And well, this is the same thing as this, right? Because cosine theta plus I sine theta equals to my e to the power of I theta. So if I assume that theta is going to be the angle pi, that's 180 degrees, for those of you who are still not familiar with radians, if theta is equal to pi, then here I'm going to be able to write cos pi times I sine pi equal to I pi, equal to e to the power of I pi, sorry. Now what's going to happen here? Cosine of pi is going to be minus 1, and sine of pi is going to be 0 times I that goes away. And I end up with this equation. Okay, nothing great here. But ultimately, if I take this minus 1 and move it to the other side, this is what I'm going to end up with. And this thing here is considered the most beautiful expression in maths. It's not easy to think why, but think of what's actually in this equation. Realize there's nothing else than these important and very transcendental numbers. Thank you very much for watching. I'll see you in class. Goodbye.